So, good afternoon, everyone. Today we are here for the optical fiber sensors live session 8. I am going to discuss about mostly the remaining thing in the phase sensing modulation, and we'll discuss about V8 contents. So, moving forwards toward the content. First, I'll just briefly introduce what are the things it's inside the um, VKit uh, optical fiber sensor VKit content, and after that we'll move towards the question answer session. So the first thing is the optomechanical blueprint. As we know that we have already discussed so many things regarding phase sensing modulation and how to rectify those things and what are the sources we need to use for the different distance sensing and various distance sensing. Then also discuss about the um, uh, several parameters. So now we are going to discuss about mainly on interferometric fiber optic gyroscope. So this gyroscope is quite um, sophisticated set system which usually used in uh, air airplanes of lights to navigate the system very in a very um, smoothly. So based on the magnetic or electrical components, it is very much possible that it can be having some kind of fluctuations uh, while it is flying from the one place to another. But this kind of interferometric optical system based gyroscope doesn't have such kind of influential uh, problem with this. So here you can see the image of that the gyroscope where it contains mainly the optical fiber, the fiber optic sensing coil, which is connected with the 50-50 direction coupler in so many layers. Then there will be light propagation in clockwise and counterclockwise, tracing the evolution of the navigational instrument from a fundamental physical phenomena to a precision engineered system. So the for the precision spectrum, if you see that for the navigation requirement dictates extreme error tolerance, such as these scales are given here for short range tacticals like a missile. In missile, the flight duration is almost in few minutes, and the precision which is required is approximately 10 degree per hour. Similarly, for the commercial aviation application, which is an airline usually, and this is like hour few hours. So here the precision requires is 0.01 degree per hour. For the space navigation, it will be interplanetary or in this interspace. So there, this kind of precision requirement is very high, which is 0 point very like requirement is very high, 0.0001 degree per hour. So as you can see that the precision is increasing towards the space navigation. So if you see that to achieve the commercial aviation precision, which is 0.1 degree per hour, an optional sensor must reliably detect phase shifts as infinite small as 4 to the power 10 to the power 4 into 10 to the power 9 radians. Now the thing is, in this gyroscope, what are the things and what is happening inside? So the fundamental physics is the Sagnac effect, where the system at rest, it will be having the clockwise and counterclockwise, both are matching together at the same place. But while system rotating, then what is happening? The finishing line move away from the wave and physical path is lengthened. So the minor perturbation also can change the change the phase, and according to that we'll get the measurement, or the it is very useful for the navigation because of this phase shift. So rotation creates a fundamental physical path length difference, and the optical wave arise at different times, generating a measurable interference phase shift. So you can see here that both wave transfer the exact same distance and arise simultaneously. Path length difference is zero. Finish line move towards wave. Physical path is shortened. Finish line move away from the wave. Physical path is lengthened. Baseline architecture. The passive interferometer. So in a passive interferometer there will be a 50-50 splitter, and there will be 4 ports, and you can see here that how the cross coupling shift happens, which is a pi by 2 phase shift, and passive state is a theta phase shift. So in a counterclockwise, if it is port 1 to 2 and the loop is 3 to 1, then the accumulated phase shift at rest is pi by 2 total, and this is partial state phase theta phase shift. Similarly counterclockwise also, the port is moving towards 1 to 3, loop in a loop 3 to 1 2 to 1, and that's why we are getting the again the accumulated phase shift approximately pi by 2 total. And so there are system bugs. So first system bug I'm going to discuss here. Because both path accumulates the exact same phase shift at rest, they perfectly constructively interfere. The baseline design cannot measure directly or microscopic changes. So for that, what we need to go, how to solve this issue is the quadrature dilemma, designing the sensitivity. So there is a in this slide there is a uh, plot between the phase difference versus output intensity, and it is mentioned in a few zones, 3 zones. The dead zone, this is the dead zone, which is a maxima. At zero rotation the slope is entirely flat. Small rotation causes virtually zero change in light intensity. The sensor is functionally deaf. Second is the engineering challenge. How do we artificially push identical light wave to the quadrature point when they share the exact same physical path? So this is another engineering challenge. The optimal zone. This is the optimal zone, which is near the below to the the midpoint, mid of the curvature, um, which is called a quadrature point. At exactly pi by 2, the slope is steepest and perfectly linear. Microscopic rotation trigger massive, highly readable intensity change here in this point. So that's why this quadrature dilemma is very important, and quadrature point is very important for this kind of sensitive instrument. Then uh, here a part of the gyroscope has shown what are the components are there. So here it's mentioned the dynamic biasing of this particular instrument, where it is estimated to the time through the time. So in this um, model, there is a light source, then port 1 and port 2, and there are port 1, port 2, and this port 1 and port 3 are connected with the PGT phase modulator. This is a 50-50 splitter, and this is in a loop, Sagnac loop it is connected. So if you see here the topographic wave diagram, so it is time versus the phase applied radiance. So the phase which is um, moving from pi by 2, minus pi by 2, plus pi by 2, the CW wave passes PGT, receives plus pi Okay, so we were discussing about the pi by 2 phase shift, and um, here is the round trip transmit time, which is time 1 to time 2, t1 to t2, one full cycle, and the switching is in a 5 kilohertz switching rate, and this point is CW wave passes PGT, receives plus pi by 2 phase shift, then PGT switches state, a counterclockwise wave reaches PGT after transmit, receives minus pi by 2 phase shift. So the patch is here is by toggling the phase shift perfectly in sync with the light's round trip transmit time. Engineering stick with the wave into the permanent state of quadrature, extracting maximum rotational sensitivity. Scaling to extremes, there will be a sensitive lever. So to scaling to extreme, the phase shift, which will be equal to 4 pi into RL divided by lambda into Vg into rotation rate. So to achieve the microscopic rotation rate, which is 10 to the power minus 3 degree per hour, is mechanically amplified into the readable 10 to the power minus 9 radian phase shift. To do that, we need to play with the loop radius constant, which is too large and the device becomes too bulky for aircraft integration. Then loop radius will be 10 centimeter. Then the second thing, fiber length, which will be 200 meter, and the advantage is optical fiber can be tightly coiled n times, heavily amplify the baseline SAGNET sensitivity. Then the last one is wavelength lambda. Standard telecommunications wavelength, which is 1.5 micrometers, can be used. Then this gyroscope has the defense ensemble, contains these parameters. Um, a perfect physical principle must survive an aircraft physical world diagnostic countermeasure matrix. So the thing is, the physical threat whatever they are there, then the resulting error associated with that, and then engineering countermeasure to the physical threat. First physical threat is Rayleigh backscattering. Rayleigh backscattering is resulting into the false wave mixing 341 degree per hour, catastrophic error, low coherence LED source. Then second is thermal gradients, time varying phase asymmetry across fiber layers, quadrupolar winding sequence. Then the third one is magnetic fields, Faraday effect, non-reciprocal polarization rotation, permeability shielding, and PM fiber core, short noise limit, photon arrival randomness, optimal power tuning, which is 100 microwatt. So with this engineering countermeasure, it can be ruled out. The second bug is coherence radiance backscattering. So when the light is propagating in a clockwise, it will also backscatter in a counterclockwise manner. This backscatter perfectly mimics the rotation signal, beating against the actual CCW wave and creating catastrophic false phase interference. And it seems like this is a very bad thing for the any flight or any aviation industry if you are using this gyro magnetic sensor. In a 200-meter fiber using a highly coherent laser, backscattering generates 0.035 radians of noise, and the result is 341 degree per hour rotational error, which is 5 order times of the magnitude worse than the commercial aviation report. To resolve this, the coherence corundum, usually it's a high coherent laser that makes the problem with a highly coherent laser. DAB laser allows backscatter from anywhere in the entire 200-meter loop to coherently interfere with the primary wave. The sensor is blinded by its own echoes. To avoid this circumstance, low coherence LED, the solution is very basic, or uh, moving from the costlier DAB laser to uh, basic LED, low coherent LED. So the patch, an intentionally incoherent light source, drops the rotational error from 341 degree per hour to fraction of degree. That is one of the advantages to use the low coherence LED. Moving towards the next thing, that is thermal gradients and quadrupole winding. So if you see that if it is a coil, counterclockwise and clockwise are uh, has the sequential winding, there is a problem with that is thermal gradient will be different, for a temperature gradient will be there. So if wound sequentially, the inner CW layers are at a completely different temperature than the outer CCW layers. This physical thermal asymmetry creates a false phase shift over time. Then next thing, that is quadrupole winding, which is having the three there are four layers. One layer will the counterclockwise, which is a clockwise layer, mentioned in the blue. uh, this one. Then layer second layers, which is counterclockwise layer, orange. Then the third layer, which is clockwise, and the last one is the counterclockwise again. So the 1441 winding pattern perfectly balances the spatial distribution of the CW and the CCW paths. Both waves experience the exact same thermal gradient, mechanically cancelling out temperature noise. Final adjustment should be done by the polarization and short noise. So the polarization we can play with the PM fiber, that is the thing we have discussed already. Then Earth's magnetic field permanently shielded outer layer, if it is there, then magnetic field twist the polarization state of light. Shielding blocks the external flux, while the elliptical core geometry mechanically locks the polarization state in place. Moving towards the next thing, which is the short noise limit. Too little light, which is equal to sensor cannot read signal. Too much light trigger nonlinear curve effect and random photon arrival noise. Engineer precisely tune the power of the optimal balance point. Constrain short noise equivalent rotation to the commercial tolerance, which is 0.01 degree per hour. So till now we have discussed about the problems and the solution for that, for this optical geometry, optical gyroscope. So um, so this interferometric fiber optical gyromagnetic gyrometric has few things. Okay, so the first thing is broadband LED source. So the broadband LED source has the low thermal coherence, excuse me, 100 micrometer length, neutralizes Rayleigh backscattering. Then there is a splitter, 50-50 splitter, which is taking the signal to the PZT, taking and bringing back the signal from the PZT phase modulator. 500 kHz Hawking law, the wave precisely at the pi by 2 quadrature point for maximum sensitivity. Moving towards the next thing, which is 200 meters full length, and turns mathematically amplifies the fundamental segment sensitivity equation, which is quadrupole winding 1441 fiber layering perfectly neutralizes external thermal gradient. Then the fiber PM fiber core elliptically internal geometry immunize the signal against polarization wandering caused by the Faraday effect. Conclusion: what begins as a deep, environmentally vulnerable physical theory is transformed through layers of igneous engineering into one of the humanity's most precise navigational instruments. So now this is the question answer time. We'll take 5 minutes break, and after that we'll come back and start this. So here is the question answer session. First question is, in a static Sagnac interferometer with a 50-50 splitter, what is the interference state of the light returning to the output to the input port P1? Please let me know your answer. So option is quadrature interference, option B is constructive interference, option D is destructive interference, and option D is complete polarization extinction. So here is the correct answer, which is constructive interference. And why is it so? It's because at the input port, both the clockwise and counterclockwise experience a total phase shift that results in a zero relative difference, acting as a mirror. Going towards the next thing, which is, for a commercial aircraft to navigate accurately between cities, what level of precision is typically required for the gyroscope? So we have already discussed about this. This is the correct answer is 0.01 degree per hour is required for the commercial aircraft. Moving towards the next thing, which is, which formula correctly represents the Sagnac phase shift del phi in a fiber coil with n turns, the radius r and the fiber length L? So the question is the correct formula. So we have already discussed about this one as well. This is the correct answer for this. 4 pi r l omega divided by nu g lambda. The third question is, why is it difficult to maintain a quadrature bias in a Sagnac interferometer compared with a Mach-Zehnder interferometer? So why it is too difficult? Because the Mach-Zehnder, it's quite different from the Mach-Zehnder. It is a common path interferometer where both waves experience the same static phase shifts. The next question, to achieve dynamic biasing in a IFOG using a phase generator carrier PGC, the modulation frequency FM should ideally be set to A 1 by 2t, where t is the round trip time, B a frequency much lower than the 1 by f noise floor, C the optical frequency nu of the source laser, and D 1 by t, where the t is the round trip time. So what is that correct answer here? So the modulation frequency should be ideally set to the 1 by 2 t, where the t is the round trip time. This frequency ensures that the phase modulator state changes while the wave in mid-transmit, creating a necessary phase difference between counter propagation components. Moving towards the next question, how does the use of a low coherence light source helps mitigate coherent length backscattering CRB by shifting the backscatter light to a different frequency, B by increasing the total power reaching the detector, C by ensuring backscatter light is only coherent with the signal over very short distance LC, by eliminating density fluctuations in the fiber core. So to mitigate coherent ray length backscattering, which can be by ensuring backscatter light is only coherent with the signal over a very short distance. Moving towards the next question, what is the primary purpose of quadrupole winding in a construction of an optical fiber gyroscope coil? A. To prevent the Faraday from rotating the polarization. B. To increase the numerical aperture of the fiber. C. To minimize phase error caused by time varying temperature gradient across the coil. Or D. To ensuring the physical size of the gyroscope. What's the correct answer here? So the quadrupole winding in a construction of the optical fiber gyroscope, that is the primary purpose is primary purpose of quadrupole winding is to minimize phase error caused by time varying temperature gradient across the coil. Moving towards the next thing, in the context of IFOG noise, the short noise limited phase deviation del phi RMS is inversely proportional to the square root of which parameter? The optical power at the receiver PT, the fiber length L, the Planck constant H, the coil radius R. The correct answer, the optical power at the receiver PT. So the short noise scales with root PT. Sorry. Making the noise equivalent to phase proportion. So if it is equivalent to the phase proportional to inversely proportional to PT, then this is the correct answer. That's why this is the correct answer. Going towards the last question, why is the Faraday effect considered non-reciprocal in a fiber optic gyroscope? So option A is it changes the frequency of the light. B. It only affects the clockwise propagation wave. C. The rotation of polarization depends on the direction of light propagation related to the magnetic field. And the last one is it only occurs in single mode fiber, not PM fiber. So the correct answer is the rotation of polarization depend on the direction of light propagation relative to the magnetic field. That's why it is non-reciprocal. So today's live session will stop here, and we'll meet for the live session 9 tomorrow, next week. Thank you so much for joining.